Okay, guys. Um, I'm happy to be back, kind of helping you guys out. We're gonna have to kind of work through the first couple of lectures. I actually feed off of y'all being right in front of me, and so I'm a little bit at a loss when I'm just speaking to my computer and just assuming that y'all are there, and sort of just looking at this cute little document camera that I have. But I'm eager to help you guys out in terms of your understanding of what's going on in calculus. Part of the reason why I went ahead and started a lot of the calculus themes at the end of pre-cal. I hope that y'all are doing well. But let's go ahead and get started. I obviously have a PDF version of the book that y'all are going to be using. It's a really good book. I chose it a couple of years ago. Now it basically runs in the same order as a lot of the books, but James Stewart has a very good handle on how to explain things. And so remember in Algebra 2, the first day, I held up the book and I said, "This is a text." And everybody said, "Book." And I said, "Books are meant to be," and everybody said, "Read." And that was, of course, the correct answer. The textbook should be read. It is a great resource, which is why I went through all the trouble of actually changing from the book that we were using to this particular one. Now, before I belabor all of that, let's go ahead and just jump right in. Y'all do have an advantage compared to a whole lot of calculus students around America, because I did introduce a lot of these themes last year to you guys. So a lot of this should wind up being very familiar, and so we're going to go ahead and focus on a lot of that. Now, from what I've gathered, y'all have started chapter 2, which is the investigation of limits. Okay? Now, you've got to remember that limits are not just the details. Limits are the sum and substance of what calculus is all about. In fact, all the way back to Archimedes in the first couple of, and people after him, the first couple of centuries BC, they actually got very close to inventing calculus. The only thing that really stood between what they were doing and calculus was the limit process. Now, the limit process winds up being incredibly cool and actually incredibly helpful. And the reason is the two things that I actually showed you last year. Now, if you remember, I showed you this animation from Wolfram Demonstrations. It was on the tangent line problem. And we've talked about, in Algebra 2 and Pre-Cal, we talked about slope. Slope is obviously how steep the line is. But more generally, slope is a pictorial representation of a rate of change. How fast one thing is changing with respect to something else. Now, if that rate of change is constant, like you have somebody is driving at 50 miles per hour with their cruise control on in their car, that is a rate of change because it is miles per hour. How fast is distance, miles, changing with respect to time, hours. But that rate of change is not itself changing, okay? You're not accelerating, you're not decelerating, you are going the same speed, and therefore you have what is called a constant rate of change. Now, if you have a constant rate of change, that is usually shown graphically as a linear function. So we talked about slopes of lines. What we failed to talk about in any detail before we got to calculus was the slope of curves. The slope of curves winds up being a little bit more difficult to discuss because the rate of change itself changes. Okay? So what happens when we deal with a curve is we have to employ limits to actually get at what we're trying to get at. And here's the reason why. Okay? Now, if I have a curve Okay, and I have a curve that does something like, oh, let's have fun, let's kind of do it like that, or something like that, like a cubic. Okay, and let's say that I want the rate of change right here. Okay, and we'll call that x, and its corresponding output, of course, is f of x. Okay, but I'm going to have a hard time getting the slope right here at x f of x. So I want to get a good estimation. I want to approximate that slope right there. So what I need to do is I need to find another point over here, and instead of calling that something different, we'll actually label this distance right here and call the distance between x and whatever this is h. So here we can call it x plus h, right? And that over here, the corresponding output is f of x plus h, and that should look very, very familiar. That's just standard function notation. And basically what happens is I draw what's called a secant line. Now, a secant line should be something that you remember not only from our discussions, but from geometry, right? A secant line, kind of like a chord across a circle, is something that intersects it more than once, okay? Now, that is not a very good approximation. We can see right here that whatever the slope is right here at x f of x, it's negative. And obviously the slope of this, although moderately positive, is still positive, right? And so what we actually want to do is we actually want to take this point right here and we want to move it that way, okay? So we will put right here a new x plus h with a new h value, okay, and of course a new corresponding output value. Now this is not the best, but at least it has an advantage over the previous because it's at least negative, right? Can y'all pick up on the fact that that's blue? I'm trying to do that whole changing colors thing that I used to do with the dry erase markers on the board. Well, that's a better approximation, but wouldn't I get a better approximation if I actually took that and I actually made another one that's even closer, okay? Well, what happens here is I'm trying to get at the actual slope here at x f of x by taking this second point through which the secant line runs and actually drawing it back towards that original one. And the closer and closer and closer and closer and closer I get, the better and better approximation I get. And that's why I showed you this approximation here. And now notice here is your h value. This q point right here is your x f of x. This p point is your this is your x plus h, f of x plus h. And the great thing about Wolfram is that it shows, and calculus is mathematics of change, it shows the change, which is just wonderful, okay? And so we see the fact that h is getting smaller, and boom, the moment that h collapses and p winds up being the same as q, we wind up getting not a secant line, but a tangent line. And the slope of the tangent line at the point of tangency is the slope of the curve as well, okay? But here's the problem. If you didn't have limits, you would not be able to calculate that, okay? Because remember, limits are the mathematics of approach. And if I'm dealing with mathematics of approach, I have to if I'm dealing with mathematics of equality instead of mathematics of approach, whatever your x plus h, f of x plus h is here, the slope of the secant line, okay, is equal to, and of course the slope formula we invoke, y2 minus y1 over x2 minus x1. So change in y over change in x. But what we have here, because we're dealing with function notation, winds up being just a little bit easier. Yeah, minus x, okay? But the denominator simplifies, right? And we wind up getting f of x plus h minus f of x over h, because basically once you free up the x plus h from those parentheses, because You know, like I've said before, those parentheses aren't doing anything. They're window dressing, right? They're just performing the associative task. They're grouping terms. We get this. Well, when h is equal to 0, okay, when h is equal to 0, we get f of x plus 0 minus f of x over 0, or 0 over 0. That is absolutely nonsensical, okay, which is why things like this are referred to as indeterminate. Indeterminate, okay? You cannot determine the value of this particular expression because it's 0 over 0. So what I'm saying is that if it's mathematics of equality, you have a problem because you wind up dividing by 0. The genius of limits is it allows you to divide by 0 and not get indeterminate. It allows you to divide by 0 and get an actual value, okay? Now the same thing occurs, or something analogous occurs, when I'm dealing with areas under curves. And of course, this is sort of a foreshadowing to the second part of calculus. This is, of course, integral calculus. So when we're finding rates of change here, secant lines to tangent lines, this is what's called differential calculus, okay? And differential calculus here allows me functionally to divide by 0 without getting 0. The great thing about this is integral calculus. Limits allow me in integral calculus to multiply by 0 without getting 0. So I may have misspoken just a second ago. Differential calculus, limits allow me to divide by 0 without getting an undefined value. In integral calculus, they allow me to multiply by 0 without getting 0, okay? So let's go ahead and put this in motion. Let's go ahead and do a right point Riemann sum, since that's actually what we wound up doing a whole lot of in order to simplify things last year. And what I'm going to do is I'm going to put this in motion. Now remember is that the approximation of the area under the curve is the sum of all of the areas of the rectangles. But in order to make a better approximation, I have to get more rectangles. So that moment I went from 4 rectangles to 10 rectangles, and you see the fact that there's less overage right here over the curve. There's less of it over the curve. So it's a better approximation. Okay, I go from 10 to, let's see what the mouse click gives us, 17, and I have less overage. Okay, but you got to remember that what you're doing is you're summing up the areas. An area, by its very nature, is a product, okay? It is width times height of all of these rectangles. So what happens when you actually start taking the width of these towards 0? The number of cross-sections, the number of subdivisions winds up going to infinity, but the width of each cross-section winds up going to 0. So what happens is that integral calculus is not about rates of change. It is about accumulating things that are of a variable nature. And when you start, if this were a straight line instead of a curve, finding the area underneath it would be easy. It would be geometry. It would be a triangle, right? The difficulty comes with the fact that it curves, okay? And so we have to use integral calculus. And of course, the areas wind up being these heights, but the area of each individual cross-section is getting smaller and smaller and smaller. So your width, the width of each cross-section is going to 0. And that's the genius of limits when it's applied to integral calculus, is the fact that you are multiplying by 0 and you are not getting 0, okay? Now that's the significance of why we're dealing with limits. That is why this whole thing is really, really important, and why it's important that you understand limits. On top of the fact that you know how much I hate teaching to a test, but the AP exam will ask you questions about limits, and even ask you questions about limits as they apply to both derivatives, rates of change, and integrals, accumulation. Okay, Well, since this is my first time to record and try and post for you guys, I'm going to go ahead and click off on this one. As we keep going, I'm going to try and get the files to be longer, and I just don't know how it's going to work in terms of uploading larger and larger files. So I'm going to go ahead and click off, and then I'm going to record another video for you this evening, getting a little bit into our review of dealing with limits interpreted graphically, and perhaps moving a little bit on even into dealing with limits evaluated analytically according to notation and techniques of changing the form. So I hope that was helpful, guys. Remember that I set up a Twitter feed, I set up a blog, I set up a specific email address so that this could be as interactive as possible, despite the fact that I'm thousands of miles away and we have a time difference. But please, please, please avail yourself of all of the resources. I've always urged you to do that. Ask any question that you want to, and the questions that are not specific to you, the questions that I find really revelatory, I will of course try to include in upcoming videos in order to flesh out our understanding of this beast that we call calculus. Alright guys, until next time, when we will have more fun with math.